Hey calculus students, because we kind of had to rush through the lesson in class today, since your book presented both the disk method and the shell method in one lesson, I'm going to go ahead and talk about them a little more and do a couple more examples so that you can watch this video to help you with your homework and learning the content. So we talked about, let's talk about the disk method again first. Okay, remember the disk method and the shell method were two methods for finding the area of a solid of revolution. Okay, so suppose we have a function of x. Maybe that looks like that. And we want to find the volume that we get when we revolve that function around the, in this case, the x-axis. Okay, so that shape that we get would look something like that here. The lowest value of x is 0, but let's just call it a, so we'll make it general, and then the highest value is b. So as we said, we wanted to, for the disk method, add a number of approximating disks of this volume. And the way that we obtain those disks is by rotating individual approximating rectangles around the axis of rotation, which in this case is the x-axis. A lot of times in my diagrams, I'll extend the axis of rotation and then draw a nice little rotation thing around it so we can see in this diagram where the figure is being rotated. Alright, so if we kind of zoom in on this rectangle, we're used to seeing rectangles where we know the height of this rectangle is f of x. So the height of the rectangle is f of x. The width of the rectangle is delta x, which depends on how many rectangles we are using to approximate the area. So that means that for the disk itself that we're using to approximate the whole volume, the radius is given by the height of the function, and the width of the disk is given by delta x. So the volume of this cylindrical disk, which I'm going to write as delta V, the volume of that cylindrical disk is going to be the area of the base, or the face of this cylinder, which is pi times the radius squared, times the height, which is in this case delta x. So in order to find the entire volume, I would want to take the limit of the increments of volume as delta x goes to 0. That gives me the integral, in this case from a to b, of pi times f of x squared times dx. So this is our volume for the disk method. This is if our axis of revolution is horizontal. If our axis of revolution is vertical, then I would just flip this whole thing on its side and get the integral. Here, let's draw another diagram so it's not confusing. My axis of revolution is the vertical axis, and I have a similar function that looks like that. Now my disks, my approximating disks look like that. So instead of having a dx, or a delta x, I have a delta y, and instead of having a function f of x, I have some function of y. I'll call it g of y. That gives me the radius at each point. And then let's say that the height starts from a point C and ends at a point D. Then the volume would be the integral from C to D of pi now times g of y squared. And I'll take the integral with respect to y. So that is for a vertical axis of revolution. Okay, so let's look at an example using a function. Our function is going to be, let's do the square root of sine of x. Square root of sine of x. And we're going to go from 0 to pi. So here's our function. F of x equals the square root of sine of x. So when we revolve this shape around the x-axis, we get kind of this pill shape, like a pill-shaped object, or maybe like a football or a rugby ball shaped object. Here is an approximating disk for the volume, which means that the approximating rectangle is given here. Okay, so the volume of this object is the integral from 0 to pi at any given approximating disk. The height of that disk, or excuse me, the radius of that disk is f of x, which I'll substitute in there in a second. The width of that disk is delta x. When we take the integral, it goes to dx. So the volume then is the integral from 0 to pi of pi times the square root of sine of x squared times dx, or rather the integral from 0 to pi of pi times sine of x dx. It really is the square root of sine of x squared should be the absolute value, but sine of x is positive everywhere on that interval, so we'll just write sine of x. So then the volume is given by pi times the integral from 0 to pi of sine of x dx, which is pi times the antiderivative of sine of x evaluated at 0 and pi. The antiderivative of sine of x is negative cosine x. So we get pi times 1 plus 1, which is 2 pi. So the volume of this solid is 2 pi. All right, let's look at an example of a function with a hole in the middle. So we call this the washer method, because the approximating disks have a hole in the middle, and so they're not really disks anymore, but they take more of a washer shape like that. So if there's our area, which is going to be for this problem, and here's our axis of rotation, our approximating disks become approximating washers. This whole figure, this volume, would look like a bowl, kind of, with no bottom, and the sides of the bowl are rounded all the way around. So that's what this volume would look like. Cross-section would look like that. Okay. In my textbook, this figure is not given by a function. Let's do the functions. Let's see. Let's do an area bounded by the functions y equals square root of x and y equals x squared. So here's y equals the square root of x, here's y equals x squared. So here's the area between those two curves, and we want to rotate this area around the x-axis. So we get a shape that looks something like that. That's a little, it's an okay drawing. All right. So our approximating washers have an inner radius and an outer radius. I mislabeled the inner radius. Inner radius and the outer radius. Oh gosh. So the volume then of one of these approximating washers is going to be the volume of the right cylinder that is formed by the outer radius minus the volume of the right cylinder that represents the hole in the middle times the height of the cylinders, which in this case is delta x. So the incremental volume is given by let's see, it would be pi times the big radius squared times delta x. So that's the volume of the outer cylinder minus the volume of the inner cylinder. And so if we factor out the pi and the delta x, we get pi times r squared times the major radius squared minus the minor radius squared times delta x. And so the volume for the shell method is the integral from wherever it starts, let's say a, to wherever it ends, let's say b, of pi times the differences in the radii squared times dx, which is the height. Okay, so let's do that for this particular example. The inner radius of this function is the distance from the axis of rotation, which is the x-axis, to the function y equals x squared. So our minor radius, r of x, is x squared. Then our major radius, r of x, is the function on top, which is the square root of x. We're going to integrate from 0 to this intersection. Where do these functions intersect? They intersect where the square root of x is equal to x squared, or where x is equal to x cubed, or where x minus x cubed is equal to 0. That happens when x is equal to 1. So this is the point 1, 1. So the volume of this solid of rotation is given by pi times the integral from 0 to 1. I move my pi outside of, let's see, the square root of x, the major radius, minus the minor radius, both squared. My integral is taken with respect to x. That's pi times the integral of, let's just simplify this as x minus x to the 4th dx, which is pi times the antiderivative, x squared over 2 minus x to the 5th over 5 from 1 to 0, which is, just giving a little bit of algebra, 3 pi over 10. So that is the disk method and the washer method. Let's do one where it might be advantageous to take the integral with respect to y. Let's find the volume of the solid of rotation formed by revolving the region bounded by the graphs of x squared plus 1 and let's see, the lines y equals 0, x equals 0, and x equals 1. So y equals 0 is the x-axis, x equals 0 is the y-axis, and x equals 1 is right here. So this is the area that we're going to revolve, and we're going to revolve it around the y-axis. This method is going to be, or this example is going to be contrasted to another example in the next section on the shell method. Okay. So the volume of rotation that we get looks like this, where we have sort of an empty bowl shape inside of a solid volume, maybe like a mortar, if you know what a mortar and pestle is. Our solid of revolution looks something like that. So in order to revolve around the y-axis, we need to take washers that have a horizontal shape. Okay, we're going to have washers above this point, which is, or above this line, which is y equals 1. And then we'll have disks below that. Okay, so we're actually going to need two different integrals to compute this volume. So let's split this into two parts. I'm going to call the upper part V1 and the bottom part V2. For V2, we're going to use the washer method. And for V1, we're going to use the, or excuse me, for V2, we're going to use the disk method. Okay, so for that approximating rectangle in V1, the minor radius is given by the function x squared plus 1. In order to take, I'm going to need to take the integral with respect to y. So I'm going to need to write this as a function of y. So I need to solve this. Equation for x. I can subtract 1 from both sides and then take the square root to get x equals the square root of y minus 1. So that's my minor radius. My major radius is just 1 because this line is x equals 1. And so for V1, I'm going to have the integral from 1 up to the place where x squared plus 1 intersects the line x equals 1, which is 2, right? If I plug in x equals 1, I get 2 times pi times the inner radius squared, which is y minus 1 squared, square root of y minus 1 squared, minus the outer radius squared. So we have 1 squared. And the integral is going to be taken with respect to y. And then volume 2 is just an ordinary right cylinder. So I'm not even going to use an integral to compute that volume. I know that the base has an area of pi r squared, which is pi times the radius 1 squared, so it's just pi, and then that's going to be times the height. So using the formula pi r squared h for a right cylinder, I get that the volume 2 is just pi times 1 squared times 1, so it's just pi. So my volume altogether is V1 plus V2, which is the integral from 1 to 2 of pi times the square root of y minus 1 squared is y minus 1 minus 1, another 1, with respect to y plus pi. So I get the integral from times pi from 1 to 2 and looking back I see I've made a mistake. Oops. This needs to be my major radius, this needs to be my minor radius. Remember, mistakes only count if you don't catch them. Boop. My major radius was 1, my minor radius was the square root of y minus 1 squared. So this needs to be the opposite as well. So it should be 1 minus, here we go, y minus 1. There we go. So 1 minus y minus 1 will give us 2 minus y dy plus pi. Sorry, I was looking at something in my book. This pi coming from volume 2. And so I get that the volume is pi. Let's do the antiderivative with respect to y. So I get 2y minus y squared over 2 from 2 to 1 plus pi, which gives me pi plus, that's this pi, plus pi times 4 minus 2 minus 2 plus 1/2, which altogether simplifies to give me 3 pi over 2. Okay, so there's an example using both the washer method and the disk method in a single example with an integral taken with respect to y. I'm going to cut this video off here because it's getting kind of long, and I will do some examples of the shell method in the next video.